Hello, welcome to R for Psychology. I'm Dr. Andy Hales at the University of Mississippi, and in this video we're going to look at how to run a one-way analysis of variance in R. So to begin, we're going to be using a cluster of packages we're already familiar with, and also two new ones. And we won't need these to run the ANOVA, but later when we do follow-up tests, the affix package and EM means packages are going to come in handy. So as always, we'll be reading in the data from the web, and then just to simplify things here, I'm selecting the columns we're going to be working with and getting rid of missing data just to make things a little simpler to work with. So when we run that, we see we have our data set, which has 8 variables. We've got a participant ID column, and we will be needing that later. And then we have these 8 survey responses asking people about their levels of basically different indicators of well-being. And in this study, people were randomly assigned to recall an event. And there were 3 separate conditions. So there was a control condition where people might have been asked to write about something trivial, like maybe what they had for breakfast. There's also an inclusion condition where people are asked to think about a time they had a conversation with someone else who paid attention to them. And then we have this phubbing condition where we ask people to recall a time they were talking to somebody and that person started ignoring them using their phone instead. And so the question here is whether the condition that they were randomly assigned to recall has any measurable effect on the well-being that they reported feeling at the time that that happened. So since we have 3 conditions, you'll recognize this is a situation where we'd use an analysis of variance. For starters, we need to compute our dependent variable. Don't worry about how we're doing this. This computing variables was covered in an earlier video. For this example, to move things along, let's assume we've already checked the reliability and looked at the distribution of this variable. So when we run this, we have a new variable in our data set. All the way over here on the right, we have recalled well-being, and that is the average of people's responses to these 8 items asking about their feelings. I'm sorry, that was actually not 8 items. I believe it was 7. So that formed an average, and it's represented on the right here. We're calling it recalled well-being, and that is our dependent variable in the analysis here. Okay, so before we go and run the ANOVA, we want to do some basic descriptives to see what we're working with. Now, we randomly assigned people to the condition that they were in, so we would expect a roughly equal number of people in each condition. Using the table function here and giving it the name of our independent variable, we can see the frequency of cases in each of the 3 conditions, and we can also see that we have no missing values for this variable. And we can see it's approximately equal, so we are good to proceed. We can also look at the means and standard deviations for our dependent variable, and here I've grouped it by the condition so that we can see mean, standard deviation, and the number of cases for the recalled well-being variable for each of our 3 conditions. And so we've got the basic descriptives down here of means and standard deviations. That's good to know. It's also numeric. A graph would be a little more intuitive here just to get an immediate sense of what may or may not be going on with this data. So again, this is not a ggplot class, but if you'll trust that the following code does what it's supposed to, you'll see that we get a plot showing approximately how scores are distributed on these variables. And you can see this is sort of a cartoon example here. We've got, let me scoot out of the way just a little bit here. We've got a pretty whopping effect. The inclusion and control conditions look like they have plenty of well-being, everyone's happy there, but in this phubbing condition, at least when people are recalling how they felt at the time, there's a visible drop-off. Is it significant? Well, overall, if we want to know if a condition has an omnibus effect, that's a job for ANOVA. So there's 2 ways we can do this. I'm going to start with the method that you're probably not going to use a lot in practice, at least when you have some follow-up tests to do. But it's easy, and so it's worth knowing. That's using this AOV function in base R. And so we're going to run this ANOVA using this information on the right here, and we're going to save it to an object called myANOVA. You can call it anything, and once we've saved it, we can summarize it and see what the actual result is. Now, I just want to call your attention to the way I've set this up on the right here. This is using what's called formula notation, and I'm telling it the dependent variable is recalled well-being. And then the squiggly sign says, essentially, we want to predict recalled well-being from the variable on the right, which happens to be condition. And so just going back to our data set to remind ourselves, condition is this categorical variable, recalled well-being is this continuous variable. And then we need to give it the name of our data set, which is coincidentally data. And so we can run and create that object and look at a summary of it. And we have an ANOVA table formatted in the familiar fashion here. We have our top line showing condition, so that would be the model values. So we have 2 model degrees of freedom. We have 83.68 model sums of squares, and we have the mean squared for the model, and the computed F value is a whopping 28. And our P value here is very, very small, so small in fact it's shown with scientific notation. This means we'd need to move the decimal place over 8 spaces in order to interpret this, so there would be 7 zeros before the 1 here. So our P value is 0.000001. It's a very strong effect, and that matches what we can see with our own eyes looking at the graph here. This is a very, very strong effect. Now, when you report a hypothesis test, you usually want to include an effect size, and the effect size for a one-way ANOVA would be a partial eta squared, and you'll notice that's not included in the table. We could compute it ourselves. It's not so tricky. We would simply take the model sums of squares divided by the total sums of squares, so we could compute 83.68 plus 64.17, that's our total sums of squares, and then we do a little division and we get our sums of squares. Or we could just use the other method, which on top of being easier to work with for planned contrasts and post hoc tests, also includes the effect size measure. So let's go ahead and proceed to method 2 then. Here, again, we're gonna be running an ANOVA, and we're going to be assigning it to an object called myANOVA. And we're going to use AOV_EZ to compute this ANOVA. And here, unlike earlier, we need to give it the name of a unique identifying column for each participant. And in our case, we have that. It's this participant row that says a unique number for each participant. And then we give it the name of the dependent variable. And for the independent variable, we assign that to this argument here called between equals the name of our independent variable. Give it the name of the data set, and then down here I mentioned we get the effect size. This is because here we're telling it to give us the effect size equals partial eta squared. So when we run all that and look at a summary of the object, here we get the same information. It's condensed it down. It's assuming that we don't want to read the error term information. And so it focuses our attention straight on the main test result of the hypothesis test. And again, we can see we get the same F value, we get the same P value, but here you'll see partial eta squared, that's our effect size. And the treatment, the condition variable here explains a whopping 57% of the variance in people's recalled levels of well-being. That is a cartoonishly large effect size, which would of course explain why the p-value is so tiny in this particular case. So there you have it. That's how you do a one-way ANOVA in R. In the next video, we'll look at how to say something more specific about which conditions are actually different from which others. So I will see you then.